Alright, so this is part 2 of lecture 11. We're going to start with the proof of this theorem about the Frenet apparatus of an isometric image, basically saying the Frenet frame pushes forward in the natural way with a little, well, I don't know if it's not really a problem, but one little caveat there, the determinant appears in the torsion and the binormal, so if you have an isometry which is not built with a rotation but built with a rotor reflection, you could flip the binormal and hence change positive torsion to negative torsion. Okay, so the proof is largely based on Theorem 2.22 we proved before. So first of all, the unit tangents for alpha and alpha bar are defined. T of s, of course, is alpha prime of s, right? And T bar of s is equal to alpha bar prime of s, but that, by definition, by construction, is alpha composed, f composed with alpha rather, prime of s. But Theorem 2.22 told us that that was in fact the push forward of alpha prime of s, right? So there you have it. That's the push forward of T of s, and of course that holds for all s, hence the push forward of the tangent gets us to the bar tangent bar. There's one down. Next, we have to think about the Frenet normals. Okay, so how do we define the Frenet normal? Well, in terms of curvature, right? Well, the curvature we defined to be what? It was the magnitude of alpha prime prime, right? And the curvature bar would be the magnitude of alpha bar prime prime, but hey, wait a second. That's the magnitude of f composed with alpha prime prime, but hey, wait a second. That is the magnitude of the push forward under f of alpha prime prime, again by Theorem 2.3.22. And, well, that is what? That's, oh, bummer. Yeah. Oh. Okay. Oh. I'm lost all of a sudden. Oh, idiot. Sorry. But we had a theorem which was that, remember, because the isometry preserves the length of the acceleration as well. So that's the length of the acceleration, but hey, that is exactly curvature. So there we have the curvature bar as curvature. Alright. I was lost, but now I'm found. Woohoo! Alright, now, so there's that. Getting back to the Frenet normals, n is, of course, 1 over the curvature times alpha prime prime, and n bar is 1 over the bar curvature alpha bar prime prime, right? But let's see here, that's really 1 over the curvature. I think it's, I mean, we know curvature bar is equal to curvature, so I can leave it curvature. And that is, of course, f composed with alpha bar, f composed with alpha, rather, prime prime, which, by the way, is 1 over the curvature, the push forward of alpha prime prime, but we can bring the curvature inside, push forward of alpha prime prime over the curvature, but you can recognize that as the push forward of n. There you have it. Thus, n bar is in fact the push forward of n. Okay, That leaves us the binormal and torsion. So next, consider B is equal to T cross N, and B bar is T bar cross N bar. All right, that's the definition of the Frenet frame. So if we consider B bar is equal to T bar cross N bar, well, we just proved that that's the push forward of T crossed with the push forward of N. And then by theorem 3.33, we already know that that's the determinant of the push forward and the push forward of the cross product of T and N. But the push forward of the cross product of T and N is exactly the push forward of B. So that's the determinant of the push forward times F push forward B. And what do you know? That's what we set out to prove. Okay, good. Then finally, torsion. Well, the torsion is equal to minus B prime dot N, and the torsion bar is equal to minus B bar prime dot N bar, right? And so, of course, we have that B prime dot N is equal to, oh, I think I'm missing a, oh, no, I'm not. B prime dot N, remember, this is the other thing we have from theorem 3.33, the dot product is preserved, so like B prime dot N, push forward of B prime, is equal to the dot product of that with N is the dot product of the push forward of B prime with the push forward of N. I get it. I'll say it eventually. But a little lemma says that that's really the push forward of B parentheses prime dot the push forward of N. All right, and so that is the determinant of F star B bar prime dot N bar, which of course is the determinant of F star tau bar. And of course this was, oh, I think I'm missing a minus. There's a minus. This is not tau, this is minus tau bar. Okay, so that's where my minus 1 comes in, I forgot to write. And this is minus the torsion. So there you go. There you have it. The torsion is equal to minus, is equal to the determinant of the isometry times the torsion of the transform curve. I probably said that wrong. Okay, anyway, you can see that this proof is a simple combination of the things we have worked hard to establish in previous lectures, and it's very nice how it all fits together. So let's work an example. I wanted to give an example here which was not too laborious. So here's Helix is always my go-to. So suppose you have alpha of S equal to, I'm going to do R cosine alpha S, R sine alpha S, and then let's see here, M alpha S. My alpha, oh, alpha, what a horrible choice of notation. Wow. That's stupid. Good grief. Let's do something. Let's choose a different label for let's maybe make it a gamma. Gamma. Alright, so gamma 1 over the square root of r squared plus m squared will do nicely. Okay, just to keep me from writing that again and again and again. So I'm going to study a simple isometry. The isometry I want to study is just the just switches. So f of xyz is equal to yx and leave z alone. Oh no, Isaac wants to show me what he found. Alright, what did you find? What did you find? What is it? What did you find?
Daniel found this for me.
You found that?
No, Daniel found it for me.
Oh wow, that's exciting.
And he can hold a bean.
You hold a bean?
Yeah, he's holding a bean.
What is this? Let me see. Let's see what this is. He's holding a bean. Oh, what is this?
The Legend Next.
A Legend Next. Oh, okay. All right. Well, I'm going to give you that back.
Yeah.
Okay. Very good. Very good. So, here's a very nice simple isometry.
Legend Next at Joshua's house.
Oh, you're going to watch Legend Next at Joshua's house? That'd be awesome. Yeah.
Probably.
Probably. Okay. Good. 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 So let's set alpha bar of S. I hope he's home. Yeah. Of S equal to and I decided to invent yet another notation. Theta is equal to gamma S. That will save me a little bit more writing. So with that notation, this is r cosine theta, r sine theta, m theta. All right. And then F composed of alpha bar will then be, it just puts the r sine theta here, it puts the r cosine theta over here, and it leaves m theta alone. All right. So then you can calculate, of course, t bar, alpha bar prime of S, and that would give me, so differentiating, that brings out a gamma, right? So r gamma cosine theta u1 minus r gamma sine theta u2 plus m gamma u3, right? Since d theta ds is gamma. And so oh, this is, yeah, I was about to say, do I need to normalize this? No, I don't, right? Notice the length, and this is by not an accident. I mean, I made this happen. The length of t bar, right, is equal to r squared gamma squared, cosine squared plus cosine squared is 1, and then plus m squared gamma squared, right? But that's r squared plus m squared divided by r squared plus m squared, because gamma squared is 1 over r squared plus m squared. So as you can see, it is in fact arc length parametrized. Okay, so then alpha bar prime of S is what? It is minus r gamma squared sine theta u1 minus r gamma squared cosine theta u2, and this term is 0 because it's constant when I differentiate it, 0. And as you can see, the magnitude of alpha bar prime of S, all right, is equal to what? Well, it is equal to r gamma squared, because cosine squared plus sine squared is 1. But what is that? Well, that's r over r squared plus m squared. That is the curvature of the isometric image. Recognize that alpha is the standard helix we studied before. So I've just showed you that the curvature of the isometric image of the standard helix, in fact, is the same as the curvature of the standard helix. So the curvature is not changed by an isometry. And likewise, you can calculate the binormal, 1 over the square root of r squared plus m squared. Take the cross product of oh, sorry, I never wrote the normal yet. The normal, this tells me that the normal is normal bar is just equal to minus sine theta u1 minus cosine theta u2, okay? So if you take the cross product of the normal bar with t bar, take the cross product of these two guys, they get you down to here, right? And a short calculation will show that that's 1 over the square root of r squared plus m squared times m cosine theta u1 minus m sine theta u2 minus ru3. All right? And so if we calculate b prime, we get what? Again, this is gamma, right? So we get m, minus m gamma squared sine theta u1 minus m gamma squared cosine theta u2, and that differentiates to 0 again, right? So then when you calculate b bar prime dot n bar, what do you get? Well, you get sine squared, cosine squared, right? You notice that minus minus gives you plus, and so what you're going to get is you're going to get m gamma squared, right? Which of course is m over r squared plus m squared. Right. Now remember, this is not the torsion. You have to put a minus on that to get the, well, torsion bar, I should say. So t bar, torsion bar, is equal to minus that, right? And you can see, in fact, that is equal to minus the torsion for the alpha curve. But this is not surprising because the determinant of the isometry we're looking at is the determinant of the, well, if it switches y and x, right? So it's the matrix, I think, is this. And that r, of course, has -1. All right? So the torsion need not be preserved. It can flip signs, but the curvature will be preserved by an isometry. That's it. I mean, that's moral of the story here. All right, so this brings us to our definition, finally, of congruence. We had a notion of congruence since high school geometry. Congruence being this idea that, we talk about the congruence of two triangles. If they have the same length, sides, and same angles, they're said to be congruent, right? And now we have a definition of congruence which will work for curves which maybe don't even have anything so nice and quaint as a side or an angle, right? They're curves. They're much more general objects. So here's congruence of parametrized curves. And here it is. We say alpha I to R3 and beta I to R3. They're both arc length parameterized, okay? Oh, no, I don't. Excuse me. I do not assume arc length parameterization. Oopsie, oopsie, oopsie. I do assume they have the same domain. All right. These are congruent. Are congruent if there exists an isometry F for which beta is equal to F composed with alpha. All right. So just to, so I do think this, of course, says then, since beta prime is equal to F composed with alpha prime, and the length of the velocity is preserved under an isometry, this will say that these curves have the same speed. That's one of the things here. So it seems to me there's some more general notion of congruence which could allow for different domains and maybe varying speeds which gave you the same point set, but anyway, this is a good starting point for congruence, or it's, maybe a good ending point, I don't know. So an example, here's an example, beta of t equal to, I'll write it out so you can appreciate the awfulness of the formula, c1r cosine t plus c2r sine t plus c3 mt minus 1 plus 3 over root 6, comma, C3 r cosine t plus C3 r sine t minus 2C3 mt minus 2, comma, C2 r cosine t plus C1 r sine t plus C3 mt minus 3 over root 6, close parentheses, where C1 is equal to 1 over the root 6, and, oh, plus 1/2, sorry, excuse me, and C2 is equal to 1 over root 6 minus 1/2, and finally C3, 1 over root 6 are constants. So what is this curve? Well, in fact, this is the standard helix. Actually, it's not the standard helix, right? It's the isometric image, I should say, isometric image of this of the standard helix with radius r and slope m. What I did was I took the isometry we built before by, remember we built that isometry to take the one frame to the other. Let's see, where was that? Back in lecture, what was it? What was it? Oh, wait a minute, it was this lecture, wasn't it? Yeah. I think it was this lecture. I'll find it eventually. Oh man! Where'd that thing go? Oh, where did I do that? Oh, schnuckers. Oh, I know, I projected it, didn't I? So it's back on my, anyway, so basically I took the, just to get to the point here, this isometry, I took that isometry, and then I just plugged in the standard helix, and out popped this formula. But I know by the previous theorem that it has the same curvature and torsion as the standard helix. But my point to you here really is just that you really can't hope, I don't think you can reasonably hope, just looking at the parametric formulas for a curve, to really identify its true geometric character, right? Now if I took these awful formulas and I somehow managed to calculate the curvature and torsion correctly, and I got, they're both constants, you know, and oh look, I recognize this. This is the, you know, curvature and torsion of the standard helix. Then I'd be in business. But you see, it's really, you need something to rely on besides the parametric formulas to discover the true geometric nature of the curve. That's the point here, is that curvature and torsion tell you which curve you're looking at. Not so much the formulas. Although you may be, I mean, I think I would hope if I write this formula, right? I would hope that if I wrote this formula, you could recognize this as a helix that wraps around the z-axis, right? It's not arc length parameterized, fine, but that's, you know, the helix. But certainly the formula doesn't have to be so nice. All right. Where was I? Sorry. So that brings us to our next definition, which is that of parallel curves. What does it mean for two curves to be parallel? So, I mean, you know what it means to be parallel for lines, right? They don't ever intersect again. One way to think about it. But we'll see the perils of that thought as we go on in this course. But definition. We say alpha and beta, both from I to R3, right, are parallel. I'll just use like that. if there exists P in R3 for which beta of t is equal to alpha of t plus P for all t and I. So that means you can take the one curve, right? And you can get the other. It won't be successful here. But the point is, if you take this point, you can get to this point. If you take that point, you can get to that point, right? If you take this point, you can get to this point. And to get from there to there, you just add P, right? You add P. You add P. And these two curves, right, are parallel. All right. I think you know it when you see it, but I wonder if we could have defined it before, right? Now, that brings us to a proposition, which will be useful to us. 3.3.9, and the proof is really simple. Parametrized curves alpha and beta are parallel if and only if alpha prime of t is equal to beta prime of t for all t and I. Moreover, if alpha is parallel to beta and there exists some t naught in their domains, all right, for which what? For which alpha of t naught is equal to beta t naught, then in fact they're the same curve. All right. So let's look at the proof. Is it's really close, very close to that theorem we proved before about a vector field being constant along a curve, or if the derivative, if the velocity is 0, it's a line. If the acceleration is, or if the acceleration is 0, it's a line. If the velocity is 0, it's just a point. Remember. But anyway, here it is, proof. So if we have beta of t is equal to alpha of t plus p. So what I'm doing is I'm going to assume alpha is parallel to beta to start with, all right? Then what? Differentiate. Beta prime of t is equal to alpha prime of t, right? And that's true for all t. Okay, so I don't know. There's not much to say here. Let's say that I is equal to the domain of alpha, which is the same as the domain of beta, fine, for all t and I. So differentiation gives you that the derivatives are equal. Conversely, if alpha prime of t is equal to beta prime of t for all t and I, then what that really means, of course, I guess fine, I can admit, this is really the sum, you know, j equals 1 to n, well, 3. This can be done in Rn, obviously. The alpha j dt, where that's the component, you know, partial xj alpha t, right? And this is, how to say this? Well, this is, you know, when we say alpha prime of t is equal to beta prime of t, we're really talking, we're assuming that they're at the same point, right? So if alpha of t and beta t were at different points, we're just comparing the vector parts, right? So, I guess to gloss over, I mean, to get across this idea, you could just say instead of using this, I'm going to use, say, uj, and so that's equal to a sum, j equals 1 to 3, d beta j dt uj. But you notice here I have to I really am moving. There's some kind of push forward going on here to be more technical. Anyway, the point here, when you can get through this jibber jabber, you just have d alpha j dt is equal to d beta j dt for j equals to 1, 2, and 3. Hence, integrating. And we do assume that the domain is an interval, which means that you can integrate and just get a constant, right? One constant. So we get alpha j is equal to beta j of t plus some constant, which I will call p sub j. And of course, when you drop and you look at what that gives you in terms of the curves, that's alpha of t is equal to beta of t plus p. And perhaps I have exchanged, no, well, sorry, I put my beta and alpha on the wrong side. Oh no. But that's easy enough to fix, right? So I'm not even going to write it out. You can switch and minus. And there you go, that's the if and only if. And then finally, if alpha of t naught is equal to beta of t naught, and they're parallel, that implies that alpha of t naught is equal to beta of t naught plus p, but that's also equal to beta of t naught, right? So therefore p is equal to 0, and so thus alpha of t is equal to beta of t for all t, right? And that completes the proof. I sense a storm is coming. All right. Again, I think the cool thing about this definition is it covers much more than lines. I mean, to me, that's interesting. And there are some curious consequences to that, I would point out, that at first glance may seem wrong, but really they're not wrong. Perhaps they're just different. Well, this is a more general definition of parallel than you saw before. So one example would be something like this. Here, I'll get some honest to goodness circles going on here. So, you know, if I have this circle, like that, right? And hey, Matthew. Well, I almost made it. If I have that circle and I have this circle, I think you can agree with me by their construction, modulo the imperfections of my artistry. These circles are certainly parallel, right? If you connect their center points, that will give you the vector p. I mean, the p which you can add to the green circle to get to the red circle, or vice versa, right? So these, these parallel circles intersect. So we can have parallel curves intersecting in Euclidean space. So that's perhaps new. Alright, so what remains of this lecture is to prove Theorem 3.3.11, which says that curves are classified by curvature and torsion. I'm just going to go ahead and project that one because I'm getting tired. And I sense my children are not going to give us much more time together in peace. So here's the theorem. Close this door. Matt. Of course, he'll open it again. So here's the theorem. Theorem 3.3.11. Curves are classified by curvature and torsion R3. Arc-length parametrized curves alpha and alpha bar, going from I to R3, are congruent if and only if the curvature and the torsion agree. Well, plus or minus the torsion, all right? So the one direction of this theorem we've already proved. Theorem 3.34 showed that congruent curves have the same curvature and torsion modulo assigned. So we've already proved that this direction is true, right? So now we got to go the other direction. Suppose you've got two curves that are arc length parametrized and they have matching curvature and almost matching torsion. I'm going to present the proof in the case that the torsion of the curve and I'm going to assume that the torsions match for the given pair of curves. I'm going to leave the proof of the minus case to the reader, probably in homework. It's almost the same. O'Neill gives you a little bit more on that. Alright, so suppose that the torsion is equal to the torsion bar, and let F be the unique isometry which pushes the Frenet frame of alpha at alpha of S naught to the Frenet frame of alpha bar at alpha bar of S naught. We know we can do this by our previous theorem about push forwarding of a frame, right? They're two frames, two different points. There exists a unique isometry which push forwards the frame. I didn't prove that the isometry was unique back in that theorem, but it's easy enough to do it. You got a formula. Suppose you have two formulas, you can show they're equal. It's not a big deal. So there we go. There's this isometry F and the push forward of T bar, N bar, B bar, and well then we're just pushing forward the Frenet frame of the alpha bar curve to the Frenet frame of the alpha curve. Now I can only do this at one point to start with. All right, so I'm doing it at the point alpha of S naught, and I'm pushing it forward to the point I'm pushing it forward to the point alpha bar of S naught, right? So just to give you a picture just for a second here, just give myself a reference dot. To give you a picture here, what's going on is we've got these two curves, right? And here's alpha of S naught, and here's, say, alpha bar of S naught. We're taking and we're finding the isometry which it pushes T to T bar. It pushes, N to oops, I can't draw, N bar, and of course B. These are supposed to be equal length to B bar, right? There is some isometry which takes you from there to there, right? And in particular, the push forward of the isometry pushes the Frenet frame on one curve to the Frenet frame on the other curve. I can do that at given pair points. I can push alpha of S naught's frame to alpha bars of S naught's frame. I can't, at the start of all this, assume that I can do that at each point along the curve, but we're going to prove, in fact, that that's possible. So, in other words, if I match up the frames at one point, and if the curves have matching curvature and torsion, the Frenet-Ray equations are going to force the frames of the two curves to match up in the natural way as we go on, as we trace forward or backwards on the curve as the arc length evolves. So, alright, that's our setup for F. Oops. So we're going to apply Theorem 3.3.4 to show that the push forwards of T, N, and B solve the Frenet-Ray equations with the kappa and tau coefficients. Alright. What that then means is we have Frenet-Ray equations for the F composed with alpha and the alpha bar Frenet frame. Notice that alpha bar here is not defined to be F composed with alpha. Alpha bar is a given curve, and alpha is a given curve. F is the isometry which pushes alpha to alpha bar. Excuse me. F is the isometry which pushes alpha of S naught to alpha bar of S naught. But before the fact, we don't know anything much more than that. We just know that there's this alpha curve and this is this alpha bar curve. In principle, it could look like this, right? It could look something like there's just some curve, whatever, and this could be F composed with alpha. Now we're going to see, in fact, the Frenet-Ray equations force F composed with alpha to be alpha bar, but that's not given to us at the start of this. So let's prove it. Now, Where was I? So, since we're given that the curvature and the torsions match, we can write down the Frey equations for the push forward and the alpha bar. So out for alpha bar. Well, the push forward's coming from applying that push forward theorem, right? We push forward the Tn and B frame. So I'm getting this because I know that T prime is kappa n, right? So because of the properties of the push forward, I also get the push forward of T derivative primed is kappa times the push forward of n. So this is really coming, this, just to be clear, the reason I get that is because I know, of course, that T prime is kappa n, and I know that n prime is minus kappa T plus tau B, and of course I know that B prime is minus tau n. So I take these, right, and I get those by doing the push forward and that theorem we just proved about. The push forward, I believe, theorem. I think it's, well, anyway, I forget the number. So we have this and we have that. Now these are true just because Frey equations are true for the alpha bar as well, and we know that kappa bar is equal to the kappa and tau bar is equal to tau. All right, so we wish to show that f composed with alpha is in fact alpha bar. And we do know that f composed with alpha prime is f, the push forward of t, and we also know that alpha bar prime is t bar. So to show that f composed with alpha and alpha bar are parallel, we really just need to show that f push forward of t and t bar have the same vector parts, right? That would be true if the dot product of the push forward of t under f was dot product with t bar was 1, since they're both unit, they both have unit length. But if you try to do this directly, things don't go well. So what we do is we follow a trick that I found in O'Neill, and I don't know, is he the originator of this trick? I'm not sure. I would be interested where this argument originated, but it's a nice argument. So instead of just looking at one dot product, we look at the sum of all three, because it's really a delicate dance that happens between this set of Frey equations and that set of Frey equations, and this really neat canceling of like 6 things. So here it is. This dot product plus that product plus that dot product, these all are dot products of things of magnitude 1. So the most this could possibly be would be 3. So the smallest it could possibly be would be minus 3. All right. So you differentiate this, and you got 3 product rules, bop, 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 and that gives you this. Oops, I'm probably off frame. Oh no, I'm thankfully on frame. Almost. I caught myself in time. Yay. So you differentiate this. Of course, you get f prime dot that, push forward dot t bar prime, and so forth, right? But this we can write as that. T bar prime is kappa n bar. See, all these derivatives we can simplify by equation 3.5. And when we do that, right, when we do that, what happens? Well, let's see here if I can get it. So simplifying by equation 3.5, these guys, oops, well, if I can get both on the same page, let me see if I can get on the same, yeah, I got them. So take these and plug these into that product rule for f, and we get, you know, products, dot products of the push forward of Tn and B with n bar, t bar, and n bar. But there's, like, for example, there's an n push forward n t bar term. Where else is there a push forward n t bar term? Push forward n t bar here. So there's plus kappa, there's minus kappa, right? Next thing, how about push forward of t times n bar? Well, push forward of t times n bar, that appears here and here with a minus kappa. So those cancel. And every possible pair you look at, yeah. Oh, Matthew requests Angry Birds. Matthew cannot be ignored.
Dad?
Oh, yes, that's a dog. You got it, man.
Dad. Da.
Dog dog. Yeah.
Da.
You like the dog dog? Ah. Come on, angry birds. Here you go. Enjoy your birds. Alright, so these cancel and we get the derivative of f is 0. However, the value of f, that's for all s, alright, in the common domains of alpha and alpha bar. But f of s naught is 3, so that constant value of 3, oh man, it's loud. The constant value of 3 must be maintained for all arc length, and so we get that, in fact, the vector parts of t-bar and the push forward of, like, the push forward of f composed with alpha and alpha bar agrees for t, n, and b. But in particular, f composed with alpha and alpha bar are parallel. And then by our previous proposition on parallel curves, we conclude that f composed with alpha is actually equal to alpha bar because their vectors, their velocities match, and they share a point in common. This hypothetical Brown curve, it shares this point, and it shares the same velocity, so it's the same curve. Which then shows, in fact, that alpha and alpha bar are congruent. They're related by an isometry, and that was the, I guess you could argue, interesting direction of that theorem. Again, I leave the case that the torsions don't match to the reader. Finally, an example, if you have, let's see here, if you have an arc length parametrized curve and it has constant curvature and torsion, that's true if and only if it's a helix. Of course, this direction, if it's a helix, it has constant curvature and torsion, that we calculated before. And we found, in fact, that the curvature and torsion for this standard helix was r over r squared plus m squared, and the torsion was m over r squared plus m squared, right? Then we also saw that if we looked at the congruent, a helix which was congruent to the standard one, it also had, you know, curvature and torsion the same, well, plus or minus the m, right? So if I have an arc length parameterized curve with constant curvature and torsion, I can actually choose values for r and m, like this, all right? And if I do that, when you calculate r over r squared plus m squared, you get back kappa, and m over r squared plus m squared, you get back tau. So what that shows you then is that if you have a curve with constant curvature and torsion, then it's congruent to a helix with that r and that m. Since the helix and that mystery curve alpha have the same curvature and torsion, by the previous theorem, which basically says that we can classify curves as having matching curvature and torsion. If you have another curve and this mystery curve has constant curvature and torsion, it has to be a helix. That's it. So, or I guess in the case of torsion 0, it has to be a circle. It has to be a part of a circle. Anyway, there's one final result in this chapter, in my chapter, and of course I'm following O'Neill loosely here. I haven't proved this yet. I'm not sure how hard it is. Well, it's not too hard. It's basically the same technique we just used. I just haven't worked it out, so I don't feel like I own it yet. But we need to use it later. If you have two parameterized curve and you have a frame field E1, E2, E3 along one, and you have a frame field F1, F2, F3 along the other curve. And if you have these matching conditions, the velocity dot the frame dot the E frame is equal to the velocity of the second curve dot the frame on the second curve, the F frame. And if you have the dot products of the frames are matching, the derivative. And so these are kind of like telling you how the curve changes, the ith frame changes in the jth direction of the E frame, and the ith frame, the ith F frame changes in the direction of the jth F frame, you know? So it says, in some sense, this condition here says that the frames evolve the same way along the alpha curve and the beta curve. So it's kind of a natural thing to look at. But if that's the case, then there has to be an isometry. In other words, beta and alpha have to be congruent if that condition is met. The proof is on page 126 of O'Neill, and perhaps we'll come back to it later if we need to. It's probably worthwhile to work through that, even though I haven't yet. Well, we need this result for theorem 9.2 on page 316 to 317 O'Neill, where he uses a critical juncture to prove something about the isometry of surfaces. Say isometry of surfaces, well, what's that? Well, first we need to describe what a surface is. That's what the next part of the course is about. What is a surface? How do we define calculus on a surface? So now we have a lot. We know a lot about calculus along curves now. This pretty much concludes this part of the course. I hope you enjoyed it. I know I did. I learned some things. I'm sorry we didn't spend more time on the Minkowski aspect of kernel. I might assign you a homework problem. I worked out something recently that was pretty interesting about that. So anyway, thank you.